Welcome to G-Fun Facts Online. Imagine a laser beam that could pass straight through the entire planet, from your feet to the other side of the world, without stopping. This isn't science fiction. It's a real theoretical possibility that could change everything we know about communication, astronomy, and even the fundamental nature of reality. Today, we're talking about the neutrino laser. To understand this revolutionary idea, we first need to get to know the star of the show, the neutrino. The name itself, coined by physicist Enrico Fermi, means little neutral one. And they are little and everywhere. They are the second most abundant particle in the universe, right after photons, the particles of light. Every single second, trillions of neutrinos, most of them created by the nuclear fusion furnace of our sun, are streaming through your body, through this room, and through the entire Earth itself, completely unnoticed. So why don't we feel them? What makes neutrinos so elusive, so ghost-like? It's because they barely interact with anything. They don't care about the strong force that holds atomic nuclei together, or the electromagnetic force that governs electricity and magnetism. Neutrinos primarily interact through gravity and the weak nuclear force, which, as the name suggests, is incredibly weak. To put it in perspective, an average neutrino could travel through a solid block of lead that is 1 light-year thick before it would be stopped. Despite being so standoffish, neutrinos are incredibly important. They come in 3 flavors: electron, muon, and tau. And they have a bizarre ability to change or oscillate between these flavors as they fly through space. The discovery that neutrinos have a tiny bit of mass, something not originally predicted by the standard model of particle physics, was a monumental discovery that opened up whole new fields of research. Scientists believe these ghost particles could hold the keys to some of the biggest mysteries in cosmology, like why there's more matter than antimatter in the universe, and what the nature of dark matter might be. But studying them is a Herculean task. We build massive detectors, often containing thousands of tons of purified water, deep underground, just to shield them from other cosmic radiation and hopefully catch the 1 in a trillion neutrino that decides to interact. Producing our own beams for experiments requires gigantic particle accelerators. It's against this backdrop of immense effort and expense that the idea of a compact, tabletop neutrino laser seems so utterly groundbreaking. So how do you build a laser out of a ghost? Let's first quickly recap how a normal laser works. The word laser is an acronym for light amplification by stimulated emission of radiation. You take a collection of atoms and pump them full of energy, exciting them to a higher energy state. When one of these atoms randomly drops back to its lower energy state, it spits out a photon, a particle of light. This photon can then hit another excited atom and stimulate it to release an identical photon, a perfect clone with the same wavelength, direction, and phase. This creates a chain reaction, a cascade of identical photons, resulting in a highly focused, coherent beam of light. The secret ingredient here is the nature of photons. Photons are a type of particle called a boson. Bosons are very social. They are perfectly happy to occupy the exact same quantum state. This is what allows them to line up and form that powerful, coherent laser beam. Neutrinos, however, are a different beast entirely. They are fermions, and fermions are governed by a fundamental rule of quantum mechanics called the Pauli exclusion principle. Simply put, this principle states that no 2 identical fermions can occupy the same quantum state at the same time. They are the ultimate individualists. They refuse to be in the same state as their neighbors. This fundamental rule made the very idea of a neutrino laser, which relies on particles being in a coherent state, seem physically impossible for decades. If you can't get neutrinos to cooperate, how can you ever make a laser? This is where some incredible out-of-the-box thinking comes in. Physicists Benjamin Jones and Joseph Formaggio at MIT and the University of Texas at Arlington proposed a way to bypass this limitation entirely. Their idea doesn't use stimulated emission. Instead, it relies on a different quantum phenomenon known as superradiance. Superradiance is a process where you can coax a group of atoms to emit a burst of particles collectively and synchronously. Instead of a slow, random trickle of individual emissions, you get a single, powerful synchronized pulse. The key to achieving this is creating a truly exotic state of matter, a Bose-Einstein Condensate, or BEC. To make a BEC, you take a gas of atoms and cool it down to temperatures just fractions of a degree above absolute zero. That's colder than the deepest, darkest voids of interstellar space. At these extreme temperatures, the atoms lose their individual identities. Their quantum wave functions overlap, and they begin to behave as a single coherent quantum entity, like one giant superatom. Now for the genius part of the plan. Jones and Formaggio proposed creating a Bose-Einstein condensate not from just any atoms, but from radioactive atoms. Specifically, they suggest using an isotope called rubidium-83. This isotope decays through a process called electron capture, where a proton in the nucleus grabs an inner electron, turns into a neutron, and spits out a neutrino. Now, picture this. You have your supercooled cloud of rubidium-83 atoms, all acting as one coherent quantum object. When the first atom in this BEC decays and emits a neutrino, a strange thing happens. Because all the atoms are indistinguishable and in the same state, it becomes fundamentally impossible to know which atom just decayed. This quantum uncertainty creates a bizarre superposition of states, where atoms have both decayed and not decayed simultaneously. As more decays happen, the possible histories of which atom decayed when get hopelessly entangled. This shared quantum coherence forces the entire collection of atoms to decay in a synchronized, accelerated cascade. The normal half-life of rubidium-83 is about 86 days. In this superradiant state, a cloud of 1 million atoms would decay in just a few minutes, releasing a powerful, directional burst of neutrinos. That's not just a beam, that's a neutrino laser pulse. The researchers even considered a potential problem. When a nucleus emits a neutrino, it should recoil in the opposite direction, which could tag the decaying atom and break the coherence. But their calculations show that because the entire condensate is one quantum system, the neutrino is effectively emitted from the whole cloud at once, preserving the coherence needed for the superradiant burst. The implications of creating a compact, tabletop neutrino laser are staggering. While the beams might not be as energetic as those from giant accelerators, they would have a unique property. The neutrinos would be quantum mechanically correlated or entangled. This could be a revolutionary tool for studying the collective behavior of quantum particles, like what happens during the collapse of a dying star into a supernova. But the applications go far beyond fundamental physics. First, communication. Because neutrinos pass through matter, you could theoretically send a message straight through the Earth to a detector on the opposite side. No satellites, no fiber optic cables needed. This would be the ultimate in secure communication, perfect for contacting submarines or underground bases. Second, we could use it for geotomography. Just like an X-ray gives you a picture of your bones, a beam of neutrinos could be used to create a detailed 3D map of the Earth's interior. By seeing how the beam is affected as it passes through the planet, we could learn about the composition and density of the core and mantle in unprecedented detail, and perhaps even locate natural resources. Third, there are medical and industrial applications. The decay process that creates the neutrino beam also creates other valuable particles. A neutrino laser could become an efficient source of medical radioisotopes, the kind used in PET scans for medical imaging and cancer diagnostics. The technology could also be used to monitor nuclear reactors or verify that nuclear materials aren't being used illicitly. Some even speculate that a network of sensitive neutrino detectors, calibrated by a neutrino laser, could one day form an early warning system for earthquakes. By detecting neutrino fluxes generated by the immense pressures in the Earth's crust, though this remains highly theoretical for now, it is crucial to remember that the neutrino laser is, at this moment, a theoretical concept. The next big step is to build a tabletop experiment to prove the principle works. If it's successful, it would open the door to a whole new era of technology. The history of science is full of ideas that seemed like pure fantasy until they became reality. Einstein's theory of relativity paved the way for GPS. The discovery of the electron ushered in the age of electronics. The neutrino laser is another one of these bold, imaginative ideas that pushes the boundaries of what we think is possible. If we can bring this theoretical marvel to life, we will have finally tamed the ghost particle, turning it from an object of scientific curiosity into a powerful tool to unlock the next frontiers of discovery. The age of the neutrino may be just around the corner,